Section 1.4, and we're looking at negative and fractional indices. I'm going to do three things here. First of all, I want to give you some explanations for some of these rules and why they should be true that perhaps you haven't seen at GCSE. And then there's a bit of advice on how to deal with the nasty ones. I know from experience of teaching this topic and the same chapter that came before it on the old syllabus a number of times, this is the first place that people start really tripping up and making lots of mistakes. And then we'll do a couple of examples to go with the advice. So, explanations. First of all, consider this a to the power 3, a to the power 2, a to the power 1 or a, so a to the power 0, a to the power minus 1, a to the power minus 2. So that's a sequence, right? And we could extend it upwards and we could extend it downwards. So what are we doing here? A cubed means a times a times a. A squared means a times a. A to the power 1, well, if you look at this, I'm dividing by a to get from there to there. So if I divide by a to get to here, then a to the power 1 means a. So that kind of works, right? So, if this is a to the power of 5, a to the power of 4, a to the power of 3, a to the power of 2, a to the power of 1, to go down this sequence, I'm dividing by a. So if I divide by a again, then I'm going to get a divided by a, which is 1. So a to the power of 0, that's one explanation for why a to the power of 0 should be 1. And if you weren't ever happy that a to the power of 1 should be an a, well, again, there's our explanation. Now let's keep this going. If I divide by a, then I get 1 over a. And if I divide by a again, I get 1 over a squared. And that's our explanation for why a to the power of minus 1, a to the power of minus 2, and so on kind of logically makes sense with this pattern here. Okay, so you can start with an a, and you can call that a to the power of 1. You can times by a and go up. You can divide by a and go down, and the powers change in that way. And what we're looking at, what the powers mean, change in this way. So there's one way of thinking about it. Another way of thinking about a to the power of 0, or a to a negative power, the other sort of standard explanation, is something like this: a squared divided by a squared. Well, that is by the subtraction rule, a to the power of 0, right? 2 take away 2 is 0. But also, something divided by itself is 1, right? A squared divided by a squared is 1. So 1 is equal to that, and that is equal to a to the power of 0. So 1 is equal to a to the power of 0. And similarly, a to the power of 5 divided by a to the power of 12, well, that is a to the power of minus 7 by the subtraction rule. And also, if I deal with it as a fraction, it's 1 over a to the power of 7, right? And to see that, it's a, 5 a's on the top, 12 a's on the bottom. And if you cancel out, divide by a on top and bottom, then we should be left with 7 a's on the bottom, so 1 over a to the power of 7. So those are the two standard ways of thinking about the negatives and the fractions. And the what's left? Oh yeah, so the square roots. Well, square root of a, if you square it, or square root of a times the square root of a, then I get a, and a to the power of a half times a to the power of a half, well, by the addition rule, that is a to the power of 1, which is a. Okay, so a to the power of a half is the thing which, when you square it, when you times it by itself, you get an a. And by definition, that number must be square root of a. Okay, so explanations, advice. Two bits of advice here. This negative rule of thumb, not absolutely always, but I can't think of any examples where it's not a good idea. It's usually deal with the negative first. You deal with the negative power first, all right? So if you get something like this, 25 to the power of minus 3 over 2, do that as 1 over 25 to the power of 3 over 2. Get the negative out of the way whenever you can. Get the negative in the power out of the way first of all, and then look at what you've got left, okay? And just to make sure we've got that straight, 25 to the power of minus 3 over 2. The way I think about it is that minus sign turns into 1 over. And then everything else goes in the denominator, 25 to the power of 3 over 2, okay? And then you can worry about 25 to the power of 3 over 2 and simplify that on its own. If you've got something like 3/4 to the power of minus a half, we'll deal with the minus first. So 1 over 3/4 to the power of a half. So it's 1 over and then 3/4 to the power of a half. Okay, so you probably know that that is the same as flipping the fraction and then having a power of a half on it. If you're not familiar with that, then it's 1 over 3/4 to the power of a half, and you know, so we can if we need to, I'll just spell out the steps. This is 3 to the power of a half over 4 to the power of a half. 1 divided by that fraction is flip the second fraction upside down and times, right? So 1 times 4 to the power of a half over 3 to the power of a half, which is 4 over 3 all to the power of a half. Okay, so this is just spelling out the steps here. The minus sign, if it's a fraction, you flip the fraction upside down. If it's not a fraction, you do 1 over. But those two things are the same, right? Doing 1 over a fraction is the same as flipping the fraction upside down. So deal with the fraction first. Now the second one is where you've got something like this. We'll take this example. Now our choice here is to do 25 cubed, then square root it. Oh, then square root our answer. Or we could do the square root of 25, then cube it. Okay? Now again, rule of thumb, but think about it. If you cube something, you're going to get a bigger number. And as a rule, a bigger number is if you cube most things, you're going to get a bigger number. Obviously, if you're starting with a number smaller than 1, that's not true. But usually, if you cube something, you're going to get a bigger number. Bigger numbers are hard to deal with. So if you're trying to square root a big number, that's one way of doing it. Or you can square root, and usually you'll get a smaller answer when you're square rooted, and that's easier to deal with. So rule of thumb, if you've got a square root or a cube root, or if you've got to take a root and then do a power, do the root bit first. If you've got numbers involved, do the root bit first, because the numbers get small first, all right? So there is the explanation as to where these rules come from. That's the advice I've got for you, having taught this a number of times. And I'm going to do this example. I'm picking one of the hardest examples first of all, and let's just apply all that advice. So what did we say? Deal with the minus sign first. So flip the fraction upside down to the power of whatever's left. So there we go. Now we're going to cube root and then square. Okay, so the cube root of 512, cube root of 343. Now you might not know those cube roots off the top of your head, but let's think about it. What cube? I mean, well, first of all, it would be worth learning the cube roots up, the cube numbers up to 10. But if you don't happen to know them, well, hopefully you know that 4 cubed is 64, and 5 cubed is 125. Okay, so 6, 7, 8, 9 cubed, it's looking there, isn't it? 'Cause we know that it's 10 cubed is 1,000, right? So we know that 512 and 343 are both between 5 and 10. We've been asked to do this without a calculator, so these things must be cube numbers, okay? And if you don't recognise them, they're well, I mean, I think I've given all the clues I can. 7 cubed is 343, 8 cubed is 512, 9 cubed is 729, and 6 cubed is 216. So if we know those cube numbers, that'll help us. If we didn't know those cube numbers, though, we might be suspecting this at this point. So you might want to do 7 times 7 times 7. And if you do that, you know, 7 times 7 is 49. 49 times 7, it's not going to take us too long to do a quick column method. 28 is 4 times 7, so that's 3. 8 and 6 is 14. There we go. All right, so we can just check it, and we can do the same. In fact, just to prove the point that it doesn't take us very long to check. 4 times 8 is 32. 6 times, this is me proving it doesn't take very long, and then doing it very slowly, isn't it? 6 times 8 is 48. That's a 2. 8 and 3 is 11. 5, 1, 2. Okay, so we can check those if we need to. So what do we say? 512, cube root of that is 8. Cube root of 343 is 7. And then we need to, so we've dealt with the 3, we've got to deal with the 2, so we've got to square the top and the bottom. So 64 over 49. And we could leave it there, or we could write that as, well, 1 and 15 49ths. Either way would be fine. What else do we have to play with here as examples. Let's just have a quick flick through the examples that they've got in the book. They're applying all sorts of rules that we've seen together. Now, actually, this is the first example again, because this is the first chapter. If you're getting stuck on section 1.4, if you're getting stuck on exercise 1D, the solution is probably redo exercise 1A, 1B, 1C. Okay, have you got enough practice on those other rules? Because all that's happening now is we're combining rules that we've seen in other chapters. Sorry, not in other chapters, in other exercises. So here, for example, we're not going to see that as division, we're going to write it as one thing over the other. We're going to do these as fractional powers instead of decimals, and then we're going to apply the power rule. So let's just do that one as an example, just to see how it's actually, it might look tricky, but it's not as tricky as it looks. Let's see. Minus a quarter. Okay, so I've just rewritten it. This is example 9, part D. I've rewritten it like this. I'm going to ignore my advice this time of dealing with the minus sign first. I could deal with the minus sign first, but instead what I'm going to do is do 2 divided by 4, and that leaves a 2 on the bottom. And then I'm going to subtract here. So this is x to the power of 3 over 2, which is 1.5, minus a quarter. So 1.5 plus a quarter is 1 3/4. 1 3/4 is 7 quarters, isn't it? Okay, so x to the power of 7 quarters over 2. Not a lot we can do with that actually, so it's easier than I thought, that one. Just checking in the book, they've left it as 1.75 instead of 7 quarters. I prefer the fractions, they prefer the decimals. In this case, it doesn't particularly matter. For most of the book, fractions will be slightly better, but in that particular example, a decimal's fine. Okay, I think that's all the help I've got for you on that section. I'll continue with section 1.5 in another video.